I'm Math 65. This is the video for lesson 114, which is located on page 589 and is scheduled for Thursday, April 16th. So, is that right? Hang on just a minute. Let me make sure I gave you the right date on that. Yes, Thursday, April 16th. Sorry, just want to make sure I didn't lead you down the wrong date. Okay. So far, we have done problems in math where there's been a definite answer. For the most part, everything's had at least one, an easy answer that we could find and solve. Today, lesson 114 is going to deal with problems that either have no solution or they have multiple solutions. So that's what we're going to be dealing with today. So we're going to jump right in. And I'm using some lessons from the book because your practice problems are going to, I'm using some examples, from the book because your practice problems are going to ask you to look at these examples and answer the practice problems. So I want to make you familiar with the examples. Okay, so example number one, find two consecutive whole numbers whose sum is 8. All right, let's break down the math vocabulary there, or just vocabulary in general. Consecutive whole numbers. It's a lot of big words, right? Let's talk about consecutive. Consecutive just means it's next to each other, okay? That's all that means. Whole numbers, no decimals, okay? So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on. Those are your whole numbers. So you need to find two whole numbers that are next to each other that have a sum. We're dealing with a sum. We know when we have a sum, we are adding, that add up to 8. So two whole numbers next to each other who add up to 8. That's how we break down what all that says, okay? So I went ahead and I wrote out all our options, okay? So whole numbers that add up to, I started just with whole numbers that add up to 8. I didn't worry about the next to each other consecutive part yet. I just said, well, let me see what all my options are to get to 8. Okay, so here's my options. 0 plus 8, 1 plus 7, 2 plus 6, 3 plus 5, 4 plus 4. All of those equal 8. Okay, so all of those are options as far that like checks the box and says, okay, they are whole numbers. Sweet, got that part. Now I need to see, we need it to be consecutive. So those are whole numbers whose sum is 8. Let's check about the consecutive piece. Well, consecutive means next to each other. So when you count 0, 1, 2, for example, 1 and 2 are next to each other. 2 and 3 are next to each other. 3 and 4 are next to each other. So looking through these, are any of these next to each other? 0 and 8, no, couldn't be much further apart. 1 and 7, 2 and 6, 3 and 5. And 4 and 4 aren't really next to each other because it's the same number. So it's not a consecutive number. If it was 4 and 5 or 4 and 3, we'd be okay. So there's no real option. None of these options work to be consecutive. So we can't check that consecutive box there. So let's look at when we have consecutive numbers that are next to each other, our counting numbers, whole numbers that are next to each other, and we add them together. When you add, consecutive numbers will be, one will be odd and one will be even. Think about that. When you count 1, 2, 3, 4. 1's odd, 2's even, 3's odd, 4's even, 5's odd. When you add an odd and an even number together, when you do that, you get an odd number. Okay? 1 plus 2, 3. Odd plus even, odd. 5 plus 6. Odd 5, even 6 equals an odd 11. Okay? So 8 is an even number. So can we even add whole numbers that are consecutive and get 8? No. Because every time we add a consecutive whole number together, we're going to end up with an odd number. So this one, because none of these would work, they wouldn't check both boxes to be consecutive whole numbers that add up to 8. And we know in general There's no consecutive numbers, whole numbers that we're going to add together and get an even number. So we can't get to 8. 8's even. So this whole problem we looked at and spent all that time on, the answer is there's no solution to this. There's just no way to do it. So it's a new type of problem for us, right? We've always been able to say the answer is this. Well, this time the answer is there is no answer. Okay? So that's one type of problem you're going to deal with in this lesson. Another type of problem you're going to learn about and deal with has many answers. Let me pull that up on the screen for you. Okay. So, example 2, the length and width of a rectangle are whole numbers. If the area of the rectangle is 24 square units, what are the dimensions of the rectangle? Okay, so let's look at that. Let's remind ourselves that area equals length times width, okay? So we need to remind ourselves of that. That area is length times width. Our problem tells us that the area is 24 square units. So we have that, so we're going to just plug that into area. And then we know that 24 is going to equal some length times some width. So what are the numbers that can multiply together that equal 24? Okay, so I've already written some of those out. So we have 1 times 24 is an option. Maybe it's 1 unit long and 24 inches wide. 2 times 12 equals 24. So maybe it's 2 units long and 12 inches wide. That'd still be a rectangle. 3 times 8 would be an option. 3 units long, 8 inches wide. 4 times 6 would be an option. 4 units long, 6 inches wide. Okay, and then there would be some other options too. Think about that. Each of these you could flip because the length and the width could flip. We know that's the commutative property of multiplication. You can, because of that, but your rectangle would look different, wouldn't it? If it was 24 inches long and just 1 inch wide, it would look different, okay? Versus being 1 inch long and 24 inches wide. This one would be 24 inches long and just 1 little inch wide. Or I'm using inches, but I think actually on our problem they call it just units. Sorry, I used inches, but it's units. Okay? So they look different. So that would be another option. Each of these flipped around could be an option because it would be a different looking rectangle. Okay? So there would be multiple options. There could be 12 times 2 and 8 times 3 and 6 times 4. Okay? Each of those would be an option for that rectangle. So, whereas our first problem we did together had absolutely no solution, this problem has tons of solutions. Lots of possibilities. Okay? So, the good news is this is one of your practice problems. So if you look at it closely, it will help you with one of your practice problems. Okay? So let's keep going on that. And there's one more example that you need to understand. Okay, and this one I'm going to use your book for because I didn't want to write all that. I bring your book on screen. So I'm right here on example 3. Let me get all the words on here. Okay, example 3, page 590. There are 2 types of games at the party. Game A requires 3 players. Game B requires 2 players. If there are 12 party guests, how many of each type of game can be played so that each guest plays in only one game? Okay. These are probably my least favorite types of problems, I have to admit. I love me some math, but this one are the ones that I do not enjoy as much. Okay, so I made a little diagram here of game A and game B. The problem told me that game A requires 3 players, so I made a note of that. And the game B requires 2 players, so I went ahead and made a note of that too. So, then I need to look at, and I know I have a total of 12 people that are coming, right? Or 12 people at the party total to deal with. So I have some options. So my first option, I'm going to go with, what if all 12 people want to play game A? Okay? So if all 12 people wanted to play game A, so I'd have 12 people divided by 3 players per game, would give me 4 games here, right? So that would mean everybody who's at the party would be playing game A. And that would mean nobody would be playing game B. I'm hoping y'all can just hear me over the mower. Yeah. Let's hope so. Okay, I'll talk really loud so you can hear me over that. Okay, so that's one scenario. So let's just flip that and do the other scenario, which is, let's just say everybody wants to play game B. Well, game B I know takes 2 players, and I have a total of 12 people. So 12 people divided by 2 players per game gives me 6 games. So I know I could have 6 games. If everybody came over here and played game B, then I'd have nobody over here on game A. Okay, so that'd be 0 games there. All right, so now those are the easiest 2 to come up with, right? So now I have to look at it and determine, are there any other combinations? Well, I can say, all right, look at 3 and 2. Are there any factors of 12 that would work well with 3 and 2 people? And the one that keeps coming to mind for me is 6. What if we could divide the people up and put 6 over here on game A and 6 over here on game B? So if we did that with our 12 people and we had 6 people come over here and there's 3 players each, so I would have 6 people and divide them into 3 players each, means I would have 2 games of game A going. So that would take 6 out of my 12 people total. And I have 6 more people that can come over here and play game B. So if I have 6 players to go to game B, and there's 2 players per game, I can have 3 games going over here. Okay? And so then I have to see, are there any other solutions that I can come up with? And this is part of your practice problem D. Okay, so your practice problems, I didn't write it down, are on page 591, and there are only 4 practice problems, and 2 of them I've worked the majority of, if not all of, the problem for you. So there's your benefit for watching the video. Hope you're doing good, guys. There'll be a video coming for lesson 115 next. Bye.